To further emphasize on resonance of organic ions, this time we take ions at the benzylic position relative to a benzene ring. So we are talking about benzylic carbanion, benzylic carbocation, and benzylic radical. Let's begin with the benzylic carbanion. So this is an example of a benzylic carbanion. And if you recall, this position, the carbon that's connected directly to the benzene ring is called benzylic. The hydrogens are also benzylic. Now this benzylic carbanion is actually stabilized by resonance. Let's do that and let's indicate electron movement using KLA arrows. So we take this lone pair and then we make a double bond between these two carbon atoms, and as a result this carbon-carbon double bond must simultaneously break, and then we leave the carbanion on this carbon. If we do that, we get a second resonance structure, so something like that, where now the carbanion is on that carbon. We can continue to move electrons around. Okay, so we take that lone pair, now we make a double bond here, and therefore that CC double bond or pi bond must break at the same time. If you remember again in resonance, it's only pi electrons or pi bonds that move. If you like, charges that only move, atoms do not move. That's very, very important. If we do this, we get another resonance structure. So something like that. And we get this carbanion. We can continue to move electrons around, and we can continue to move electrons around using KLA arrows. And if we do that, we move electrons like that, and then we have to break obviously that CC double bond, leaving the lone pair or the two electrons on the carbon that's indicated. If we do that, we get this last resonance structure. So there are therefore 4 resonance structures in this case, in this benzylic carbanion, which suggests that the benzylic carbanion is stabilized by resonance. Let's now take benzylic carbocation. So a carbocation at the benzylic position. So something like that would be representative. So a positive charge on that benzylic position, a positive charge on the benzylic carbon. Now in order to do resonance, we need to delocalize electrons. We need to move that charge around. Of course, it is resonance, and again in resonance, remember, it is only pi bonds or pi electrons that move, only charges that move, atoms do not move. Hybridization does not change. Now we have to break therefore one of these carbon-carbon double bonds. So this carbon-carbon double bond, we break it, and then we move electrons that are released on that CC single bond. Now by doing so, this carbon would therefore be neutral, and as a result also this carbon would now be positively charged because it has lost its electron share. If we do that, we get another resonance structure. And now the positive charge is on that, is on that carbon. Continuing with the movement of electrons, we now move electrons in a similar way by breaking that carbon-carbon double bond, using the electrons now that are released to make a double bond between that carbon and that carbon. Why? Because that carbon is positively charged. As a result, that carbon would be neutral. This carbon would then lose its electron share, and therefore it should bear a positive charge. If we do that, we get this next resonance structure. And now that carbon has a positive charge. Moving on, we need to break that carbon-carbon double bond, releasing electrons to make a double bond between these two carbon atoms, and as a result, of course, that carbon again should be neutral then, and that carbon therefore should be positively charged because it has lost its electron share. If we do that, we get a fourth resonance structure of this benzylic carbocation. So the positive charge will be on that carbon. So these Lewis structures are possible for this benzylic carbocation in this case, which suggests that the benzylic carbocation is actually stable, and it is stable by resonance.